Today we are going to discuss about topic is discrete time Fourier transform. It is fourth unit for you. For CD sections already this topic is covered. Again anyway, also listen this one. If you know Z transform, it is very easy to learn discrete time Fourier transform. All of you know the Z transform or discrete time Fourier transform are used for analyzing these discrete time signals and discrete time systems. So already we know continuous time Fourier transform. In this continuous time Fourier transform, we analyzed the continuous time signals, continuous time systems. So it is just counterpart for whatever the continuous time signal we have, that gets to be converted into discrete time signal. And if we want to analyze the discrete time signals, we are going for discrete time Fourier transform. Usually Fourier transform means we are going to analyze the signals or systems in frequency domain. That is the main motto of using this any transform. Now, already we know the continuous time Fourier transform formula. X of t Fourier transform is x of omega. It is equal to integral minus infinity to infinity x of t into e power minus j omega t into dt. The same formula you are just modifying. Wherever we have a x of t, that x of t we are going to be replace here x of n. Yes, x of n means discrete time signal. What is the difference between continuous time signal and a discrete time signal? Suppose if we take a continuous time signal, if at any instant of time we are going to get the corresponding amplitude. But while we are coming for this discrete time sequence, we are discretized by using this sampling theorem. So the information we are going to be aware, the information available at discrete instance, that is like an integer, n equal to 0, here n takes the values 0, 1, 2, 3, and so on, and minus also, negative values also, minus 1, minus 2, minus 3. So that is the main difference between the continuous time signal and the discrete time signals. Then, what are the previous Fourier transform formula? You must know Fourier transform formula is integral. So there is a, instead of integration, we are going to be right here summation. There is an integration. We are going to be right here summation. That is the main difference between continuous time to discrete time formula. Okay. Then wherever we have a x of t in the formula, that x of t we are going to be replace here x of n. Wherever we have a e power minus j omega t, that j omega t we are going to be replace here j omega n. My sincere request is here, in this book he is following with the notation this type of omega, but whatever the omega in continuous time Fourier transform we have used, that omega you better follow. Otherwise, for E and F sections, you may follow this omega, because for the C and D sections already the topic is over. So they can follow with the general omega, whatever the omega we have. So that is the formula of discrete time Fourier transform. Now, what is the IDT of t of x of omega? IDT of, suppose after converting a time domain to discrete time to frequency domain, again we need to convert from frequency domain to time domain. So that formula is IDT of t of x of omega is equal to 1 divided by 2 pi integral minus infinity integral. That formula also I will show you inverse. Here it is now. Yes, here it is there. Now you see, what is the x of n? X of n is inverse discrete time Fourier transform. Inverse discrete time Fourier transform of x of omega is equal to x of n is equal to 1 divided by 2 pi. That interval is minus pi to plus pi, x of omega into e power j omega n into d omega. So that interval, suppose it is, maybe sometimes we can also write 0 to 2 pi or from minus pi to pi. So the spectrum of this Fourier transform, discrete time signal Fourier transform, follows the periodicity in nature. So that's why that is a fundamental period, minus pi to plus pi x of omega into e power j omega into d omega. It is the relation between x of n and x of omega. dt of t of x of n is x of omega. Inverse dt of t of x of omega is x of n. These are the general pair. Now, one second. Now, if you see when we are going to be apply this discrete time Fourier transform for all signals, is it applicable? One more thing, if you know the jet transform, I can discuss about the jet transform also here. We know for analyzing the discrete time signals or discrete time systems, the another better transform is jet transform. Suppose if we use x of n, jet transform of x of n is equal to x of z. Similar formula, n equal to minus infinity x of n into z power minus 1. The formula is here, whatever the formula we have, instead of dt of t, we are going to write z transform of x of n. It is equal to x of z is equal to summation of n equal to minus infinity x of n into z power minus 1. So what is the difference between this Z transform and discrete time Fourier transform is this DTFT is a special case for Z transform. If you know Z transform, if you have a idea about Z transform, then it is very easy to evaluate discrete time Fourier transform, because the discrete time Fourier transform is a special case for Z transform. Whenever usually Z is equal to R into e power j omega, whenever if you evaluate on unit circle, that means here what is the magnitude of Z means magnitude of R into e power j omega. So what is the magnitude of e power j omega? What is the e power j omega? Cos omega plus j sin omega. So if you take a magnitude, root of real square plus imaginary square. Root of real term is here cos. So cos square omega plus sin square omega. Okay. Hey, remove that screen. I can stop this and again I will share. So for existence of this discrete time Fourier transform, Z transform. So Z transform is DTFT is a special case for this Z transform. So here Z is equal to R into e power j omega. So the magnitude of Z is equal to R into e power j omega means cos omega plus j sin omega. If we take a magnitude of this one, root of cos square plus cos square omega plus sin square omega, it is going to be get. So magnitude of Z is equal to R. So if we take this R is equal to 1, it is going to be evaluated on unit circle. So that is the difference between సార్ అదే సార్ దాన్ని అది డిజేబుల్ చేసేదాన్ని ఏం సార్ అది వీళ్ళు మన ఏరియా బ్రాంచ్ నేను బాన్ పిల్లలు కూడా ఉంటారు సార్ వీళ్ళు అందుకని వీళ్ళు అది డిజేబుల్ చేసేయాలండి. So that is now for existence of DTFT. If you coming for existence of DTFT, like continuous time Fourier transform, it must be absolutely integrable. It must be absolutely integrable. Coming for this uh, discrete time Fourier transform, it must be absolutely summable. It must be absolutely summable. Absolutely summable means now we consider here summation of n equal to minus infinity plus infinity. This magnitude of x of n is must be less than infinity. Suppose this condition is satisfied, then only we can apply DTFT for analyzing this sequence. One more condition is summation of n equal to minus infinity infinity, magnitude of x of n whole square is less than infinity. So what is this magnitude of x of n whole square? It is nothing but energy of the signal. So we can see whether the summation of n equal to minus infinity infinity, this magnitude of x of n is less than infinity. Suppose this condition is not satisfied, you can see alternate other condition also, that is summation of n equal to minus infinity infinity, this magnitude of x of n whole square is less than infinity. So any one of this condition is satisfied, then we can apply discrete time Fourier transform easily. Okay. These properties already we discussed here. Now we are going for problems. Now coming for these problems, x of n is equal to a power n u of n. X of n is equal to a power n u of n. It is a discrete time sequence, a discrete time signal or discrete time sequence, a power n u of n. Now here a takes the values from -1 to 1, -1 less than or equal to a less than or equal to 1. Okay. Now if you first you need to see whether this sequence is absolutely summable or not. This sequence is absolutely summable or not. Now if you see the summation of n equal to minus infinity infinity, magnitude of x of n is equal to summation of n equal to minus infinity. If you write as this formula, a power n u of n whole power magnitude. Now this u of n, you know what is the u of n? U of n is a unit step sequence. It is equal to 1 for n greater than or equal to 0. U of n is equal to 1 for n greater than or equal to 0. Now n greater than or equal to 0 means what is the limits here? N takes the values from 0 to infinity. N takes the values from 0 to infinity. So substitute here n equal to 0 to infinity, then magnitude of a power n. Consider this magnitude of a power n. Now you know u of n within these limits, u of n is anyway 1. So n equal to 0 to infinity, magnitude of a power n. Now you know the harmonic series formula, n equal to 0 to infinity, a power n is 1 by 1 minus a. Here, whatever the magnitude, that magnitude right here. So the a value is, we know the a value is, it is varying between -1 to +1. So we are taking this magnitude. So whenever it must be, the value is less than 1. The value is must be, it is not equal to 1, in between -1 to +1. So definitely we are going to get some finite value. We are going to get some finite value. So whatever the given sequence, this given sequence is absolutely summable. So then we can apply DTFT for this sequence. So you consider the DTFT formula. Whatever the DTFT formula you consider. Here you see DTFT of x of n is equal to x of omega is equal to summation of n equal to minus infinity infinity x of n into e power minus j omega. It is the DTFT formula. Now, whatever the x of n, we are going to be substitute here. What is the x of n? A power n into u of n. Again here, what is the u of n? U of n is equal to 1 for n greater than or equal to 0, and it is 0 otherwise. So what is the meaning of u of n is equal to 1 for n greater than or equal to 0? N takes the values. N takes the values from 0 to infinity. So whenever it takes the values from 0 to infinity, whenever it takes the values from 0 to infinity, within these limits, this u of n is equal to 1. So n equal to 0 to infinity, a power n, this e power minus j omega n. So n equal to 0 to infinity, a power n, e power minus j omega n. Okay. So it is your formula. Now it can be right summation of n equal to 0 to infinity, a into e power minus j omega whole power n. So again, it is the harmonic series formula, n equal to 0 to infinity, a power n. That is nothing but 1 by 1 minus a. So instead of a, we have here a into e power minus j omega. So x of omega is equal to 1 by 1 minus a into e power minus j omega. Here you observe here. Observe this one. This a value must be less than, magnitude of a is less than 1. Then only it is applied. Now, if you want to draw magnitude response and phase response, if you want to draw the magnitude response and phase response, so you can take that x of omega is equal to 1 divided by 1 minus e power minus j omega. You know what is the e power minus j omega? It is equal to cos omega minus j sin omega. So 1 divided by 1 minus a into cos omega minus j sin omega. Then you multiply with minus a in this term. So you will get 1 minus a into cos omega plus minus into minus plus into j into a sin omega. Now it is a real part as well as imaginary part. Here in this book he has done a lot of rationalization, all these things. But one way is, better way is, instead of doing this analysis, lengthy analysis, my point is, what is the magnitude of this x of omega means usually, suppose if you consider numerator. In the numerator, there is no any imaginary part. Suppose there is an imaginary part, we can write root of real square plus imaginary square. So here, there is no any imaginary part. So numerator, there is no any change. Coming for denominator, if you write magnitude of x of omega, that is root of real square plus imaginary. What is the real part here? 1 minus a into cos omega. So root of 1 minus a cos omega whole square plus a into sin omega whole square. So simply, instead of doing this rationalization and multiplication, separation, all these things, simply you write, we know whenever there is a real part and there is an imaginary part, and if you want to calculate magnitude, so we can write root of real square plus imaginary square. Okay. Now, if you do like this, finally, whatever the analysis, this lengthy analysis was done, that is equal to, you expand this one, 1 minus a cos omega. After this, you will get the similar fashion, 1 minus a, this one. 1 minus a cos omega whole square plus a square. Then if you expand this one, so finally, you will get like this. 1 divided by 1 minus 2a cos omega plus a square. Instead of doing all these things, you just root of, write down real square plus imaginary square. The real square means this 1 square plus a square cos square omega minus 2a cos omega. And this one as usual sin square omega. Sin square omega plus cos square omega is 1. So like that if you do, finally you will get the magnitude of x of omega is this one. Magnitude of x of omega is this one. And coming for phase, you see again, coming for here, this one. Tan inverse of imaginary part by real part. What is the imaginary part here? Imaginary part is 0. So the phase angle is, the numerator is 0. Coming for denominator, tan inverse of imaginary part by real part. What is the imaginary part? A sin omega divided by real part is 1 minus a cos omega. So tan inverse of tan inverse of, again tan inverse of this a sin omega, you see like finally you will get like this. Tan inverse of a sin omega divided by 1 minus a cos omega. So after selecting this a value and by substituting different omega values, omega value you take 0, pi by 2, pi, 3 pi by 2, 2 pi like that. If we substitute different values of omega and if we draw the spectrum, magnitude spectrum must be a periodic in nature. So it is about any given problem, the discrete time sequence. If you want to analyze in, if you want to extract the information in frequency domain, then you need to do like this. Okay. Similarly, you take another problem. You see here, the problem is like this. Determine Fourier transform of the discrete rectangular pulse with amplitude is A and the length is L. So the rectangular pulse means, rectangular pulse means a finite number of samples are there, finite number of samples. So x of n is equal to A for 0 less than or equal to n less than or equal to L minus 1. So suppose L is equal to some 10. So what is the length of L minus 1? 9. If you count from 0, the, the total length is 10. So that is the given sequence, rectangular sequence, and it is 0 otherwise. So for this, you need to apply discrete time Fourier transform. Now, as usual, before applying the discrete time Fourier transform, you need to check whether this one is absolutely summable or not. Because the drawback of discrete time Fourier transform is it is not suitable for unstable signals. It is suitable for only stable signals. That is the difference between Z transform and discrete time Fourier transform. Suppose if we take a Z transform up to certain range of values of sigma, at least up to certain range of values of sigma, the Z transform is exist. While we are coming for this discrete time Fourier transform, it is not like that. Suppose it is absolutely summable, then only we can apply this discrete time Fourier transform. Otherwise, it is not possible to apply this discrete time Fourier transform. So that is the problem with the discrete time Fourier transform. That's why every time we need to see whether the discrete time Fourier transform is applicable or not for the given sequence we are going to be test. So what is the condition? Summation of n equal to minus infinity infinity, magnitude of x of n is less than infinity. Must be less than. So less than infinity means it must be some finite value. So you consider first what is the given data, the rectangular sequence, the limits as given. The limits as given. The limits will be given from n equal to 0 to L minus 1. Okay, n equal to 0 to L minus 1, and it is a magnitude of A because that amplitude is A. Now, if you substitute these values, A into definitely n equal to 0 కాబట్టి, if you write here 0 plus L minus 1, 0 also if you count, total length is L. So L is a finite, A is a finite, it must be less than infinity. So we can, it must be absolutely summable because it is a finite value. So we can apply this DTFT for the particular given sequence. So as usual, you write DTFT of x of n is equal to x of omega. It is the formula. DTFT of x of n is equal to x of omega is equal to summation of n equal to minus infinity infinity x of n into e power minus j omega n. Now this n equal to minus infinity infinity, you can write n equal to what are the given limits. Instead of applying the entire limits, the data in the data is given from, it takes the values, the rectangular sequence takes the values from n equal to 0 to L minus 1, n equal to 0 to L minus 1. So that's why you write here n equal to 0 to L minus 1. 1 second, I will take the attendance. One second. Now, if you apply this x of omega formula, x of omega is equal to summation of n equal to minus infinity x of n into e power minus j omega n into summation of n equal to 0 to whatever the limits has given the rectangular sequence is up to L minus 1. So n equal to 0 to L minus 1. This x of n has given that amplitude is a into e power minus j omega. Anyway, a is a constant, you write outside, and the n limits are from 0 to L minus 1, e power minus j omega whole power n. So instead of general formula for harmonic series for finite intervals, suppose there is summation of n equal to, see this formula, summation of k equal to n1 to n2, a power k is equal to a power n1 minus a power n2 plus 1 divided by 1 minus a. Here n1 is a lower limit, n2 is a upper limit. So the same formula you can write here, x of omega is equal to, instead of a, we have here e power minus j omega. So e power minus j omega, n1 is in this formula, we have it is a 0. So e power minus j omega whole power 0 minus e power minus j omega whole power, what is this one? Upper limit is infinity. What is the upper limit? No. 1 second. Not here. This one. What is the upper limit here? E power n1, it is 0. N2 is L minus 1. So L minus 1 plus 1, it is a L. So e power 0 is, a power 0 is 1. So amplitude a into 1 minus e power minus j omega L divided by 1 by 1 minus a. So instead of a, we have e power minus j omega. So 1 minus e power minus j omega. So it is the formula, it is the DTFR given finite length sequence. Now, if you want to convert it is into sine terms, you want to convert this one into sine terms, you just write this 1 into 1 is equal to e power j omega L by 2 into e power minus j omega L by 2. So e power j omega L by 2, e power minus j omega L by 2 gets cancelled. So finally we'll get 1 only. And this is also you can write e power minus j omega L by 2 into e power minus j omega L by 2. Similarly here also e power j omega by 2 into e power minus j omega by 2. This e power minus j omega, e power minus j omega by 2 into e power minus j omega by 2. And then you take this e power j omega L by 2 is a common factor. In the denominator, e power minus j omega by 2 is a common factor. And remaining terms, you will get here e power j omega L by 2 minus e power minus j omega L by 2. In the denominator also e power j omega by 2 minus e power minus j omega by 2. Just you divide both terms, numerator term, denominator with 2j, then you will get the sine term. So it is the, finally, this sine term, this sine function, we are going to convert also into sinc function, no issue. Why it is this exponential term? We take a rectangular pulse, it is exists from minus negative interval as well as positive interval, then that is not going to be get here, this phase term. Whatever the rectangular pulse we have considered, it is considered only for positive side. The standard rectangular pulse is from both negative side as well as positive side. So it is a delayed version of this whatever the considered rectangular pulse is, just a delayed version of the original rectangular pulse. That's why there is an extra, we have this phase term is getting. Now if we take a magnitude, again the magnitude is same. If we take a rectangular pulse, what is the Fourier transform of rectangular pulse, whether it is a continuous term or it is a frequency term, definitely it is a sinc function. You convert this sine function into sinc sine pi lambda by pi lambda, you write, you will get the sinc function, no issue with that. So it is about a discrete time Fourier transform of given finite length rectangular pulse. Now you can see another standard sequence, that is a determine the Fourier transform of unit step sequence. So already in the previous problems also we have written what is the u of n is. U of n is equal to 1 for n greater than or equal to 0, and it is 0 otherwise. So what is the n greater than or equal to 0? N takes the values from 0 to infinity. N takes the values from 0 to infinity, and it is 0 otherwise. So x of n is equal to u of n. So x of n is equal to 1 for n greater than or equal to 0, and it is 0 otherwise, or it is 0 elsewhere, whatever it is. Now, as usual, the formula of discrete time Fourier transform x of omega. So that is x of omega is equal to dt of k of x of n is equal to summation of n equal to minus infinity x of n into e power minus j omega n. X of omega is equal to dt of k of x of n summation of n equal to minus infinity x of n into e power minus j omega n. So what is the x of n? What is the x of n? Nothing but u of n. What is the u of n? It is n takes the values from 0 to infinity. So instead of using minus infinity to plus infinity, you can use the limits from 0 to infinity. Within these limits, what is the x of n? It is a 1. And then e power minus j omega n. So 1 anyway constant, e power minus j omega whole power n. From the harmonic series, we have a formula for harmonic series. N equal to 0 to infinity, a power n. A power n is equal to 1 by 1 minus a, 1 by 1 minus a. Magnitude of a is less than 1. 1 by 1 minus a, magnitude of a is less than 1. So if we see here that